realistic to do attacks against, for example, the compare algorithm and a hashed password, and brute force somebody's password using timing attacks remotely in a web application. They can demonstrate they can do that on a normal Java instance with something like 100 milliseconds of latency on the network, right? Those attacks are already doable without any local access. And all the academic papers that have demonstrated side channel ability on hypervisors have been between two groups that are working together, two instances, virtual machines that are working together to move data. So that's definitely an issue if you're running a multi-level security environment, like if you're the government and your cloud is going to have secret and top secret and SCI right next to each other, and you don't want two machines to conspire together to leak data across an interface. But there are no realistic attacks right now against things like pulling out RSA keys from OpenSSL and stuff like that, compared to the network stuff, which is usable. Okay, so I'm going to do a quick run through just for folks here who don't work in cloud computing environments about why it's important. Just like David said, obviously economics is a big driver in our industry these days, and security people are kind of famously impotent in the boardroom, right? And it's because for the most part, from a P&L perspective, all of us only have an L next to our name. None of us make a direct profit for our companies unless, obviously people in here, when we work for security companies, that's great. But when we work for our clients and our client is a big bank, at a big bank, IT is not the focus of their board, of their chairman and their boardroom. It's not a focus of their big executives. IT is the plumbing, right? If the chairman of the board of the bank, if his executive oak-paneled bathroom floods, then he calls a plumber, right? And if his IT breaks, he calls the IT guy. And he doesn't want to think about either the plumbing or the IT for the rest of the year unless it breaks. And because those things aren't seen as kind of core functions that add profitability to the company, IT folks and plumbers don't have a lot of ability to steer the big ship of state. And that's why regulatory compliance regimes that let you get $600 an hour outside counsel to tell the executive to do certain things, those regulatory regimes can be very powerful for security people, shouldn't be over-relied upon, like David was talking about. But anyway, there's a lot of situations where security people and IT people are saying, oh, we can't do the cloud thing because of X, Y, and Z. And the problem is that the economic arguments for using cloudifying your infrastructure, either because you own a bunch of your own machines and you want to have better utilization, or because you don't want to own your own machines, the economic benefits are pretty unbeatable. I strongly recommend folks who are interested in this stuff to go to this URL. Google ran a green infrastructure summit that actually they invited all their competitors. So Amazon and Microsoft and eBay and all these folks came to this summit and talked about all of the ways that they were greenifying their infrastructure. And this is not just we want to greenwash, we want to put a logo on our front page. Day-to-day electricity cost is one of the largest components of running a real infrastructure. And there's a thing called PUE, which is basically a measurement, and there's a bunch of different power measurements, and I don't exactly remember where PUE ends, if it ends at the CPU or ends at the motherboard. I think the PUE ends at the motherboard. So this is the ratio of the amount of power that goes into the data center versus the amount of power that's used to actually power the computers. And a typical multi-tenant commercial data center has a PUE of around 2.0. Google advertises a PUE of about 1.16, and privately they'll tell you that they're beating that in some of their newest data centers, that they only need 16% more power to run all the other crap in the data center than the actual computing. And then, like I said, there are better measurements that actually go down to how much power is going to the CPU versus the other components in the system and stuff. I don't think that counts in PUE. Things like hard drives spinning and stuff are included in the 1 versus the 1.6. But certainly this does include things like cooling, power distribution, lighting, and all that kind of stuff. This is an unbeatable thing if you're a CFO of a major tech company and somebody tells you this, that we can reduce our major ongoing expense for, a data center sounds expensive as a capital investment if you spend $1 billion to build this data center, but that's nothing compared to what it costs to run it over 20 years. And if somebody tells you through building our technology differently, we're able to get down to 1.16 versus 2, that is a competitive advantage that's very difficult to beat. And this is actually the competitive advantage that the cloud computing providers are fighting on, right? The fact that Amazon can charge you 13 cents an hour to run a small virtual machine, and smaller companies can't afford that because they don't have the economies of scale and they don't have the custom hardware and the custom data centers to support it, is one of the things that provides Amazon with a bulwark against people just going up and setting up AWS competitors. Same thing with Google. So one of the things that Google demonstrated was some of their custom hardware. This is actually 2 or 3 generations ago. But a couple of generations ago, this was the cutting edge Google hardware, which you'll see, it's just a motherboard on a tray, 2 hard drives. If you look really closely at the high res, you'll see that there's no manufacturer imprint on this motherboard, because they get the motherboard built specifically for them. You'll also see that it's massively loaded up with RAM, which tells you a little bit about how Google does their optimization of some of their speed stuff. It's because if you have 64 gigs of RAM on every single machine, you can keep a huge amount of your data actually in RAM at all times. They have a 12-volt power supply directly attached right to the motherboard, and then this black thing, which doesn't have a very good resolution. Anybody know what that black thing is? Can anybody guess? You see a red wire coming off of it? Sorry? No, the network's built right in. They have a backplane port that basically hooks up 4 gigabit network connectors up to a backplane, and the PHYs are right there on the motherboard. This is a battery. It's a 12-volt motorcycle battery, right? Google pushed the UPS to every single machine has their own UPS. And one of the things they found when they were studying why their data centers are so inefficient, because they used to buy off-the-shelf data centers, is that you get something like 110 kilovolts coming in from a big high tension power line into your data center, and then you have to step it down to what? 12 or 24 volts to run it through a bank of batteries. And then you step it up from 24 volts back up to 110, where it goes in 110 to the rack, and then this sucker steps it back down from 110 back to 12, right? And anybody here who here is a double E? Oh, come on. There's got to be some. Man. Well, if you've played with electronics, you know that one of the most inefficient things in electrical systems is the conversion of electricity, both between AC and DC, and also the major steppings of voltage. And dropping the voltage down from all the way down and then back up was incredibly inefficient and causes a huge chunk. You'll see that power distribution and backup right there, that's 22% of the problem. Right there is just the stepping and moving of power around. And so what they did is they built this custom hardware where they only have to step it down once, and there's no central UPS, there's no central generators. All of their machines have their own about 3 or 4 hours worth of power on their UPS. And why don't they have generators? Has anybody here actually had a data center where the generator turned on and didn't fail? Has anybody ever heard of a data center incident? Most of the power outages I've seen is because they're doing either testing the generators, or they had a power failure and they moved over from battery backup onto the generators and it caused a failure, right? Those systems are incredibly unreliable. In fact, that's when 211 Main went down, taking down half the startups in San Francisco. That's because they were doing a generator test. And I think Google just figures if they don't have power for more than 4 hours, they move that load onto a different data center. So it's the kind of thing you can do if you own 20 data centers. Maybe not so much for most little companies. But this, 4 or 5 years ago, this is something that Google had to go to Foxconn and get them to manufacture their motherboard custom, and had to build all their racks custom, and all that stuff had to be custom. Now you can go buy that stuff, right? Folks like Rackspace, which is now part of SGI, are commoditizing that kind of hardware simple tray with voltage conversion in one place. And you can buy these super dense racks from them. Another thing that Google did first that now you can buy off the shelf is the idea of the container data center, where you build a container where computers are so densely packed with liquid cooling that human beings can't get in. And the reason you do this in a cloud computing environment is that you never fix an individual machine, right? If a machine fails, if all of a sudden it starts throwing lots of errors, you just turn off that machine. And then you wait until that container degrades to 30 or 40% of the machines are degraded, and you take the whole container offline, you pull it off, and you unbuild and rebuild the whole thing, right? Fixing all the parts. And that's a technique that Google first did that now you can buy off the shelf. Again, I think this is also SGI. And if you have $2 million, you can go to SGI and they'll give you a shippable container with something like 80,000 cores in it. All you have to do is put it in your parking lot, give it something like 480 volt, 20 amp power hookup, and then hook up the liquid cooling to a big radiator, and then Ethernet. And all of a sudden you have a data center in a box. Like I said, the economics of this are unbeatable. So in the future, what's this mean for data centers? It means that centralized fault-tolerant storage is going away. You'll see that this guy has 2 hard drives on it. These guys have 6 hard drives. Locally attached storage, so much cheaper on a per terabyte basis. Probably the least cost-effective thing anybody buys is an EMC these days, from the ratio of what you can do it on Newegg versus what you can do. And that's because people like the idea of fault-tolerant centralized storage, where folks like Google and Amazon and those kinds of folks are using locally attached storage, and they're using a software layer to provide that level of reliability on top of the unreliable cheap hard drives that they attach. These are off-the-shelf desktop hard drives. These are not data center quality 15K SAS drives. They're 7200K Hitachis or whatever. And when they fail, they have 2 or 3 copies of that data on a software level, not on a hardware level. These aren't even RAID 1. I think they're not even RAID. It's a JBOD. So when the hard drive dies, it takes all of its data with it. Dedicated specialized servers are going away. The idea of, I'm going to have one server that I custom order to do this one thing. Why is it going away? Because that's not a scalable idea. If you can't scale your software without calling up Dell and having a 4-week turnaround for them to ship you a new server, then you're going to have some trouble if your organization has to be flexible. And that's why people are doing things instead of, I have one instance of Oracle on one machine, and if I want to upgrade it, I make it a bigger machine, using distributed databases that have the ability to scale out through commodity machines. Instead of 64 core, I have 4 16-core machines. And then if I want to add another 16-core machine, I already have it ready to move over from a different workload to that. Dedicated specialized network equipment is going out, and we'll talk about that in a second. And kind of the generic abstraction layer between the data center and the hardware. Standard 22-inch square hole racks with 110 volts will be around for a long time, but the big boys aren't using it anymore. And at some point, we are, as normal human beings that don't own our own data centers, we'll be able to rent space with different abstraction layers that are much more efficient. Maybe data centers where there's 12 volts to every tray, and people are using standardized tray sizes. Or perhaps I bring my own rack into the data center, and then I get my 480 volts into that rack, and whatever power distribution and cooling I want to do within that, I do. But one of the things that you'll see if you watch those videos, hot aisle, cold aisle cooling, incredibly inefficient. Also a huge pain in the butt, right? I hate taking off my winter jacket when I go from the front of the computers to the back of the computers, and all of a sudden it's 87 degrees, and I go back and it's 52 degrees, and I've got my meat hanging from a hook, to be cooled down. It turns out that's a very inefficient way of cooling computers. So people are either doing direct cooling right there in the rack with liquid into the rack or liquid into the individual machines, which is much more efficient. Also, people are doing things like building data centers in cold places and then opening up louvers on the side and just blowing cold air through it, so you don't need air conditioning. There's a reason a lot, people like Microsoft and Yahoo and Google are building lots of places on lakes up in Canada or the Pacific Northwest. What are the 2 reasons? One was cooling. What's the other reason? Cheap power, yes. If you ever get on Google Maps, look up the Dalles, D-A-L-L-E-S, Oregon. This isn't a secret. Google's talked about it. And you'll find this huge complex of data center buildings next to a hydroelectric dam. That hydroelectric dam was built just to power an aluminum smelting plant in Oregon. This is near the Oregon-Washington border, right down the river from the Hanford nuclear facility. So I wouldn't drink the water. But back in like the 20s or 30s, the New Deal, they built a power generating plant just to power an aluminum smelting plant. Of course, those jobs are in China. But then Google came around and said, hey, look, it's a hydroelectric plant that nobody's using the power from. And they just built a data center there, and they hooked it right up to the hydroelectric plant. So as long as it rains in Washington and snows in eastern and western Idaho, that Google data center gets incredibly cheap power. And then it's also nice and cold there most of the year. So air conditioning costs are very, very low. And that's kind of the future of a lot of these cloud data centers, is putting them in places that don't have earthquakes, that are cool all year and have hydroelectric power. So not very good for the California data center industry. But so things you should think about before you move. Ask yourself, why are you moving to the cloud? What security promises are you making? And try to map to those security promises some of the controls you're going to have. This is actually something you should do whenever you design a system. This isn't really threat modeling. This is threat modeling light. I don't like to use the term threat modeling with a TM behind it because it's got such a Microsoft stride connotation. Not that there's anything wrong with Microsoft, but there's a level of intensity in the threat modeling that people like Microsoft talk about that is not realistic for most people. What's a realistic threat model is sit down and think to yourself, what promises are we making